What's up? Today, I'm gonna learn about Intel Core Ultra 7. And I'm using Intel's the worst one, Intel Core i7 from 14th generation, and it is so bad, like terrible. So that's why I want to renew my PC, and also I want to learn about Core Ultra 7, also Ryzen. Let's get started.
As for the 265K, it features 8 P cores with 8 threads, as again, hyper-threading is no longer used for the Arrow Lake architecture. The P cores feature a base frequency of 3.9 GHz and a boost of 5.5 GHz, and that's a mere 2% frequency reduction when compared to the Core i7 14700K. Then there are the E cores, and in total we have 12, again with 12 threads as there is no SMT support. The cores operate at a base frequency of 3.3 GHz but can clock as high as 4.6 GHz, which is actually a 7% increase when compared to the E cores featured.
So generally, this Core Ultra 7 is better than Core i7 14th generation. That's not surprising, but I think it's just less trouble and upgraded
On the
maybe
14700K. In total, there's 30 megabytes of L3 cache and 36 megabytes of L2 cache, and that's seen when combining the L2 cache of the P and E cores. The P cores each receive 3 megabytes of L2 cache, whereas the E cores get 4 megabytes per cluster, and each cluster consists of 4 cores. Finally, the base TDP is 125 watts with a max turbo set at 250 watts. And for this, Intel is charging $395 US per 1,000 units. It's also worth noting that all K-SKU models, which are currently the only models that have been announced, support dual-channel DDR5 5600 UDIMM memory or DDR5 6400 CUDIMM memory. And in short, CUDIMM memory features a small clock driver circuit directly on the module, and this allows for more precise timings that are required at higher memory speeds. All models provide 20 PCIe 5.0 lanes and 4 PCIe 4.0 lanes, along with a direct media interface 4.0 8-lane bus to the chipset. As usual, the K-SKU parts have an unlocked clock multiplier and therefore can be overclocked. Now, for our testing, we have multiple different test systems, so rather than discuss all of the hardware and configurations, you're welcome to pause the video here and study the test system specs. And once you've done that, you can move on to the benchmark graphs. First up, let's take a look at how the 265 behaves under load. And again, for cooling, I'm using the new MSI.
So motherboard 14th. Oh, okay.
MSI has created a unique bracket that migrates the cold plate north for a 3-degree reduction in temperature, as it better targets the hotspot on these new Arrow Lake CPUs. So with the Core Liquid i360 strapped on, I loaded up the 265K with Cinebench, where we saw an average clock frequency of 4.6 GHz on the E cores and 5.2 GHz on the P cores, and this was achieved while remaining within the stock 250 watt power limit. The CPU saw a peak temperature of just 84 degrees, which is well below the 105 degree TJ max. Now for a look at the Cinebench multi-core performance, and here we see that the 265K is good for just shy of 2,200 points, making it 8% faster than the 14700K and 18% faster than the 9900X. So we're looking more at 7950X and 14900K levels of performance in this test. The single core performance is also very strong, with the P cores capable of 145 points, and that's a 4% increase from the 9900X and 14% faster than the 14700K. Now, when it comes to power consumption, the 265K consumes 218 watts, which is around the same power draw we saw from the 12900K, 14600K, 7950X, and 9950X.
Oh, so That's that's nice. Core i7 14th generation is 308 and Core Ultra 7 is 200. So 3 and 2. That's really better.
As we just saw, performance was comparable to the 7950X, so power efficiency is roughly on par with that part in this particular workload. It was also 8% faster than the 14700K, and yet here we see power consumption has been reduced by almost 100 watts, and that's an impressive 29% saving. All of that said, the more efficient Ryzen parts, such as the 7950X 3D, did deliver a similar level of performance to that of the 265K, while consuming 33% less power. Moving on to file compression performance, we see that the 265K is actually slightly slower than the 14700K, trailing by a 6% margin when using the same DDR5 7200 memory. Performance was also comparable to the 9900X.
But almost
The
same.
265K falls even further behind the 14700K when it comes to decompression performance, and this is due to a lack of SMT support. This time, using the same memory, it's 15% slower and 18% slower than the 9900X, so that's a fairly disappointing result. The Blender Open Data test has more positive results for the 265K, as here it is 7% faster than the 14700K and 8% faster than the 9900X, basically delivering 14900K like performance, so I think given the power savings that's pretty good. Now looking at the Corona 10 benchmark data, we find 14900K and 9900X like performance, making the 265K 10% faster than the 14700K. Now we have the Photoshop 2025 data, and here the new Arrow Lake CPUs are pretty underwhelming. And I'm still looking into these results, as these new CPUs should be faster in this workload, but as it stands for our configuration, the two underwhelming, given that the 265K is slower than the 14700K and therefore the 9900X. Okay, time for the gaming benchmarks, and we'll start with Star Wars Jedi Survivor, where the 265K is pretty crap, if I'm being honest, coming in behind all competing parts. Using the same DDR5 7200 memory, it was 10% slower than the 14700K, 9% slower than the 9700X, and even 6% slower than the 9900X, which isn't exactly known to be a great gaming CPU. Of course, if you are after elite levels of gaming performance, you'd be more interested in the Ryzen 7 7800X 3D, and in that comparison, the 265K is almost 30% slower. Quite well, slightly beating the 14900K and then 10% faster than the 9900X, and were really bad in our 285K review, and we suspected this could be a scheduling issue, so we disabled the E-cores within the BIOS, but that didn't seem to improve things. Yet, despite that, performance does improve when enabling the Prioritize P-cores setting under the Hybrid CPU Utilization option, boosting performance by around 15%. A lot better than what we were seeing previously, but sadly, that is still massively disappointing. Performance in Hogwarts Legacy is very mid-tier, and that is to say that the 265K is more than it is the 9700X. PC, coming in slower than the 12K, is providing 14700K light performance, making it slightly faster than the 9900X, but 7% slower than the 9700X and 15% slower than the 7800X 3D. Now I've updated our example and solution to the poor performance for this title either. The 265K is slower than even the 14600K, which meant it was...
For me, I'm not a gamer and I don't need that much frame rate, so I think it's good enough.
13% slower. Compared to the Zen 5 parts, Intel at least margin, and that meant it was slower. So a 6% margin in this example. When gaming, we see the 265K is comparable to the 9900X based on this Cyberpunk data. The only issue being the 265K didn't perform that well in this game, especially in the section that we use for benchmarking. Therefore, The Last of Us Part 1 is a better game to look at power efficiency for these Arrow Lake CPUs, and here the 265K consumed 5% less power than the 9900X for 12% more performance. So that's a great result. That said, it's not the best result Core Ultra 7 265K doesn't stack up very well, coming in 8% slower than the 14700K and 4% slower than the 9900X. And as I've said, the Ryzen 9 processor isn't a particularly good gaming CPU. It's also wild to consider that just a few months ago, you could purchase the 7800X 3D for just $340 US. And in fact, let's take a look at the cost per frame data now based on...
So, generally speaking, Ryzen is better for frame rate, and Core i7 from 14th generation is better at frame rate, but so much high energy consuming, and the new one, Core Ultra 7, is little bit less the gaming or these kind of things score, but the efficiency of energy is better, like improved. So for me, the 14th generation Core i7 is causing blue screen, so the renewing the Core Ultra 7 might be good thing for me. And I have never used Ryzen, and I think it's okay, but I'm not sure. Let me know on the comment about Ryzen.
current retail pricing. So even after finding ways to boost performance in Homeworld 3 and Cyberpunk 2077, Arrow Lake still sucks really bad for gaming, so that's fun. When it comes to value, the 265K does stack up far better than the 285K did, thanks to the fact that it costs almost 40% less while being just 5% slower across the 14 games we tested. This means it's actually quite similar to the 9900X in terms of value, slightly better even. But as I've said a few times now, if you primarily care about gaming performance, the 9900X isn't 20% better. Following on from our 285K review, things don't look too Cyberpunk numbers do or test certain games like Cyberpunk and A Plague Tale Requiem under lighter CPU loads. It'd probably be possible to produce results that allow Arrow Lake to match Raptor Lake, delivering the parity data that Intel promised us. But as I found in my 285K review, if you place these Arrow Lake CPUs under heavy load in games, for whatever reason they tend to fall in a heap, and that's exactly what we saw in A Plague Tale Requiem. Whether or not this is something Intel can address remains to be seen, but I sure hope it is, otherwise Arrow Lake is going to be an epic fail. So far, the greatest improvement for Arrow Lake can be seen when monitoring power usage, and this was always expected to be the case. We just hoped that gaming performance would be much better than it is. The 265K is more efficient than the 285K, and does reach a point where it's very similar to the 12.
I'm not sure. What is your choice? I'm not sure. How do you think? Ryzen, Intel, Core Ultra. I'm not sure about the lineup yet, but Ryzen, Intel Core Ultra 9 and 7 and 5, right? And the 265K kind of things is I'm not sure about that. These are the like maybe Core Ultra 7 and 2 or 3 lineup, or I'm not sure about the 265K Core Ultra 7. And Core Ultra 9 285K. I'm not sure. I think that that might be the Ultra 7 and the 200 blah blah blah, and higher is better, and these kind of things maybe.
12 and 16 core Ryzen models, at least the ones without 3D V-cache like the 7950X 3D, is essentially dead on arrival. Even if Intel manages to fix the gaming performance and genuinely finding parity with the 14700K, at that point you'd only be looking at 7700X like gaming performance for a 45% price premium. Of course, the productivity performance of the 265K is much better, but if you're after a good balance of gaming and productivity performance, the 7950X 3D is a much better choice at $480 US.
Oh, really? And I'm curious about the AI CPU kind of thing. I'm not sure about the name, how it's called. The using AI with the CPU.
And of course, we have the Zen 5 based X3D chips just around the corner, so parts like the 265K and 285K are facing some serious competition. As I said when wrapping up my 285K review, I fully expect Intel to iron out the kinks in the coming weeks, which it should help a bit, but I can't imagine it's going to be enough to save Arrow Lake. But I really hope I'm wrong about that. For now though, I am done with this initial review of the 265K. Let me know.
Right. I'm not sure what you thought and what did you choose? Intel Ryzen, and I think whichever it's usually alright, but I'm so sad the blue screen of Intel 14th generation. So I thought it was whichever okay, but I picked one not good one, Intel 14th generation. So I want to know. Next one, Intel Core Ultra 7 265K CPU review and benchmark vs 285 245K. I think it's the Ryzen, the 7800X3D and so on.
In this review. So the 265K again is $404, which is fitting because Error Lake value can't be found. The price has it similar to the 7900X, which is currently $400. The 7900 non-X is $370 or so, with the 9700X at $330. The 9900X is $430. AMD has this territory completely encircled with similarly priced options. The 7800X3D comes in 19% more expensive at $480 and would be less viable in production use cases we test, but far more viable in gaming scenarios. If you're only doing one of those two types of workload typically, that allows you to either ignore or focus on the 7800X3D. If you're doing both, that'd be where the 265K might make sense. Basically, if you're splitting your daily use of the computer between really heavy work type applications and gaming. If it's not beaten by Intel's own 14700K at $350 or its 13700K at $290, that would be where the 265K has a chance. And then AMD has also announced its 9800X3D, or whatever they call it, for November 7th. We're not sure what it's going to cost yet. It is very likely it's not a direct comparison unless they really surprise everyone with the pricing, just because we'd expect it to be at 7800X3D levels or higher. And that right now is $480. It's been as low as in the 300s in the past, but hasn't been there for a little while. So as a reminder, other considerations for Arrow Lake, again, include the entirely new platform. So Z890, LGA 1851 means you'd be buying into a new board. These boards are some of the most expensive we've ever seen for this class. Oh. And in some cases we've seen it can also be benefited disproportionately by higher memory speed, but that gets more expensive than potentially just buying one of the other CPUs that can cut costs and corners. As a positive though, the reduced power consumption means reduced cooler requirements as compared to Intel prior generations. It's not going to be as compared to AMD. It's lower powered, generally speaking, across the board. Some 9950X, stuff like that, are a little different. But anyway, that's kind of where it lines up, and that's it for the basics and the positioning. If you want more, Check out any of the last videos. We'll link them all in the description for you to make it easy. And otherwise, let's just get right into it this time. Our efficiency testing has been explained in depth in 2 pieces now and briefly introduced in a 3rd. To learn more about what we're doing here, check out our 285K review and our preceding video where we set up our monstrous test bench that you're looking at now. We'll start with 7-zip compression efficiency. We're just going to go with the ATX 12V and EPS 12V rails for this because we think these are the closest to accurate on our setup. The 265K ended up at 163 watts in this test, which has the efficiency at 968 MIPS per watt. That has the CPU as less efficient than the 285K, which pulled 162 watts on the same ATX 12V and EPS 12V rails, but produced a higher throughput, yielding a 1051 MIPS per watt result. AMD's 7800X 3D, 7700, 9700X, and everything else, including the 3700X from 2019, ranks above the 265K result. The 265K really is only better than the 9950X, the 2700, the 5800X, and Intel's own lineup here. In decompression efficiency, the 265K repeats its rank and falls below the 1194.9 MIPS per watt result of the 285K. The power drawn is the same since this test suite runs both consecutively and at about the same power level. The end result is that the 265K is marginally less efficient than the 245K, more meaningfully behind the 285K, and is otherwise mostly just ahead of the prior Intel CPUs. Generationally, the improvement on the 14700K is
so much information. I'm so confused. Okay.
actually good. It's 47% test. Now for gaming efficiency testing, this is still imperfect and it's something we're still developing. So we're going to keep tuning this. There'll be some changes as we continue to iterate on the gaming efficiency benchmarks. Mostly because of Asus's change to pull from the 24-pin. That's really complicated things for us. So this is what we've got. We feel pretty good about it overall. It's calibrated. We want to do some further finer tuning though, so just be aware of that. All right, so here the 265K pulled 89 watts when measuring both the ATX 12V and the EPS 12V rails. That has it similar to the 285K. We noticed during this testing an initially higher reading on the 265K. It was almost 10 watts exactly, but after troubleshooting vCore, CPU package power, and a bunch of other power numbers in the charts, we were able to isolate that 10 watts as being from a measurement tool difference on the 265K platform that we used. 14900K has a lower power
efficiency.
consumption of the 14.7 as a result of external bottlenecking, limiting CPU utilization, also binning. It can't fully be leveraged, and so that's why we see that difference there. 285K and 265K are both fully engaged, though. Dragon's Dogma 2 is up. In this one, the 265K ran at 99 FPS average, which has it 4.6% ahead of the 245K, and it has the 285K about 4 to 5 FPS ahead of the 265K. The 14700K leads the 265K by 8.6%, with the 13700K about the same. The AMD 7800X 3D is ahead by 11%, with the cheaper 5700X 3D also ahead of the 265K while running on an older, cheaper platform. The 265K is worse value than even the 245K in this particular game, and we wouldn't recommend that one either. Its low performance here is fine, with no particularly meaningful deviation from the expectation, but overall, the two now with a 7.5% uplift in frame rate, lows increased proportionally with the average. This positions the 265K as equivalent to the AMD 7700X and a bit ahead of the 7700 and 7900 non-X parts. The 7900X is functionally tied with the 265K, making it both performance and price matched in this test. K ends up sandwiched between the 14600K and 13600K as we bounce off of a K 1%. It's basically error though. The 14700K leads the 265K by 2.4%. And the 285K did well in this particular test. It managed to outrank the 14900K, leading the 265K by 5.8.
So on Premiere, Adobe Premiere, Core Ultra 9 is the best, and 14th generation i9, Core i9, and Core i7 and AMD, and Core i9 from 13th generation, and AMD, and Core Ultra 7. So I think that's not much difference on my use. but mm, it would be great. It was great if it was with that Core Ultra is better than Core i7 14th generation. Maybe the use of the energy, electric energy, and kind of things, batteries, electric power, these kind of things might connect it, but
Percent. So that's it for this one. A couple things to point out here. The 265K is, in several of the cases that we've tested, less efficient than the 285K. A couple reasons for that. One is efficiency, again, is a calculation involving the power consumed doing a task and then the actual output of that task. And so 285K performs better in those tasks. That's going to bump it positively. It is still more efficient than its predecessor from the 14th gen, but it's not always more performant. So that's kind of the trade-off. Now, in all comparisons we run, AMD is more efficient still, and that kind of wraps up that side of the efficiency equation. As we recap the charts overall, it's clear once again that the 265K is surrounded by good options on all sides. The 285K is exceptionally bad value for gaming users. It is actually impressive how bad the value is. The performance is worse than what you'd get on a $230 5700X3D in a lot of cases for the 285K, or a $480 7800X3D in all cases for gaming. And also, it costs a lot more than the 7800X3D. So that's the 285K. In non-gaming uses, there are some limited scenarios where you could make an argument for the 285K, but they are relatively rare among our test suite in terms of the value proposition. The 245K made even less sense. The production use, you make an argument for older Intel, especially with the prices coming down, but those two make the most sense depending on the budget the user has. Getting cheaper, Intel starts to make more sense. Like the 12600KF was something like $80 recently at Best Buy, so that's kind of crazy. But otherwise, that's kind of how it stacks up. And then for production use cases, again, you can make an argument in some of these applications. It's just not a sweeping victory, and Arrow Lake has external issues where Intel, as we said in the 285K review, didn't even know what it was shipping. It asserted very clearly that APO would be on by default on everything. And that's back to 13th gen. And it simply was not. And while APO has no real impact in our test suite, which is why we didn't include it here again, because like at most we were seeing.
Okay, so I got the general things. I understand the general things. And I don't know about the AI things by the CPU. And why I want to touch about that. NPC. I'm not sure how to search about that. I want to know about the AI thing, but IGP. Oh, so iGPU can be the like graphic board is maybe better. But I think if people getting Core i7 or 9 kind of thing, the Ultra 7, Ultra 9, might get the graphic board, so that might be not the great things for desktop. Maybe for laptop it would be great, but uh, I want to know ours. This month, we buy Core Ultra. Game Bench. Core Ultra 9. And I'm not sure what I can do for AI things with the CPU. Maybe just chat up and image generation kind of things, or and I'm not sure about the difference. The Core i14s and Core Ultra 7, like using stable diffusion and image and video generation. And what's the difference of the using AI? I'm not sure. Let's watch this.
If you're a streamer, content creator,
Why to upgrade to Intel Ultra Core? Core Ultra.
a gamer, or all of the above, but you're not massively into tech, or you know
Let's watch why upgrade to Intel Core Ultra.
is whatever goes into the PC just needs to work, then this video should help fill in all of the gaps you need to make. A huge thank you to Intel for sending out their Intel Core Ultra 9 285K processor, the Z890 Aorus Elite Wi-Fi 7 motherboard, and for sponsoring this video, as well as Corsair for sending out all of the components to future-proof my new streaming and work PC. Now, let's talk groundwork, because before you decide to grab a new CPU, you probably want to know what you're grabbing. That might be a little harder for folks not heavily into the PC building scene, simply because Intel have recently changed their naming conventions for their desktop CPUs. Luckily for us though, Intel has provided a handy infographic that helps explain the structure of the new Core Ultra processors alongside the previous generation, which makes it super easy to compare and gives us the ability to make a translation of sorts between the two. First off, let's look at the previous generation of processors. Here we see the Intel Core i9 4900K processor. The first section denotes Intel, which is the corporate brand, the second Core being the product brand, i9 referring to the performance tier, the 14 referring to the 14th generation of this chip, 900 which also refers to the performance tier, where i7 would be 700, i5 would be 500, but in this case i9 is 900, and then the suffix, which usually denotes what they are designed and optimized for. In this case, K refers to high performance and unlocked for overclocking. Let's take a look at the new naming scheme now, which applies to the Intel 200S series and, in theory, future CPUs. Again, you start off with the corporate brand obviously being Intel, but the product brand has now been expanded to Core Ultra, with 9 now being the performance tier, dropping the iconic I prefix. The one here is referring to the generation, as with this new brand
Oh, so this is something important.
of Intel CPUs, they've officially
Jeez.
reverted to the first generation. This first
Jeez.
began last year when Core Ultra was introduced with mobile products. At the end, we have the H suffix, which again refers to what this
Well, I want to.
first began last year when Core Ultra was introduced with mobile products. At the end, we have the H
so-
suffix, which again
Mobile products, that means some laptops with already sold, and these I heard of that these can use AI with the CPU integrated things, and that was the first generation maybe, and the desktop PC things is the second generation maybe.
and refers to what this processor is optimized and designed for. But now both the generation and the suffix and the interim numbers refer to the SKU as a whole. To help draw a comparison, the CPU that I have, which is the Intel Core Ultra 9285K, is effectively the equivalent of the Intel Core i9 14900K. If we break that down really quickly, that gives us Intel being the brand, Core Ultra being the newest product line, 9 being the highest performance commercially available, 2 referring to the second series, and K referring to the fact that this is a high performance unlocked CPU. To help draw some other comparisons, the Intel Core Ultra 7 is the equivalent of a Core i7, and the Core Ultra 5 is the equivalent of a Core i5. There's some new ones in there, and there are some differences in terms of the full set of SKUs, but generally that's a pretty good guideline. But enough about the changes to the names, let's talk about what's actually changed in the CPU and why you should be looking at this new generation of processors for your content creation needs. Especially if you haven't benefited from an upgrade in recent years. A lot of the improvements for creators that come with the Intel Core Ultra processors are centered around the fact that these chips not only have a CPU and a GPU, but they also house an NPU. Now, while you might know what those first two are,
the NPU, the AI things, right? I'm not sure about that. I don't know about that.
you may not have heard of an NPU. But basically, at its core, an NPU is a specialized processor explicitly designed for executing machine learning algorithms, which is what many brands refer to as AI. Before you panic about having an emotionless, disembodied mind hell-bent on taking over the world sat inside your PC, in this context, this kind of AI refers to the neural nets that help your PC to handle complex processes and computations and offload them from the CPU itself. Which in real people terms just means that the NPU can handle things like audio optimization, removing the background from your camera, auto framing, which allows you to move around when streaming but to always have you centered in the middle of the screen, all without having a negative effect on your streaming or gaming performance. With advanced tools becoming more and more commonplace in the world of content creation, you might be fooled into thinking that these now very approachable features are also very easy to do. But just because they're light on setup doesn't mean they aren't heavy lifts for your PC. And that's exactly the kind of thing Intel are looking to solve when it comes to this new generation of desktop processors.
So, my understanding is like separating CPU and GPU and similar things is said on NPU, so neural network, like AI things. So, like dividing the partition maybe that's the kind of things, right? So CPU is general things and GPU for graphic and NPU for AI, so-called AI kind of things. I see.
While still working towards giving you the best possible gaming experience, they're also looking at efficiencies to improve your current experience, make all the things that you currently do that much easier. While these are still pretty hefty processors, features like the NPU and the ability to be able to provide a similar gaming experience as the previous generation, but with 30% less power usage, really shows their dedication towards making things work smarter and not harder. If you're interested in the new Intel Core Ultra desktop processors and you want to find out more, not just
So new generation is less electricity, so that means less energy and less heat and less blue screen crash. I think that's the things.
about how this helps you with content creation, but also gaming and work. I've left a link in the description for you to see more, but in the meantime, stay safe, stay awesome, and I'll see you all soon.
And NPC. I want to learn about the NPC things. NPC. I'm not sure how. What's the benefit of NPC? Now, like maybe not that used yet. In future, it will be used mainly, but maybe not yet. That kind of things. Let's watch this. Intel Core Ultra processor. let's watch Intel Core Ultra processor explained in 60 seconds.
Here are 4 things to know about Intel Core Ultra processors, codenamed Meteor Lake. First, these processors are the driving force of the AI PC. The new chips feature Intel's first integrated neural processing unit for a range of AI workloads. Second, Core Ultra processors are the first PC chips built on Intel 4 process technology. Their tiled architecture features multiple chips built with different flavors of silicon, connected by Intel's advanced packaging technology called Foveros. Third, Core Ultra processors are the most power-efficient Intel's ever built. They contain 2 kinds of cores. P-cores tackle high-performance tasks. E-cores quickly handle mundane jobs with little power, stretching your battery life by hours. Finally, built-in Intel Arc graphics boost 3D graphics performance for smoother, more power-efficient gaming. Intel Core Ultra processors will lay the foundation for PC innovation for years to come.
I'm sure.
Technology called
Intel user. Extraordinary. Ultra. Oh, let's watch this. Unlock the extraordinary. The Intel Core Ultra 200V series.
Building a great PC is not done overnight. It takes time to refine the technology, optimize the architecture, and deliver a product which is flexible and performant. Every year, we have innovated our chips to make them more powerful, more efficient, more intelligent, to create our most innovative processor yet. Introducing the latest Intel Core Ultra 200V series processor, with all the PC features you know and love, and the AI capabilities that will revolutionize the way you use your computer. Intel Core Ultra features revolutionary core performance, breakthrough power efficiency, extraordinary graphics performance, and incredible AI capabilities. When it comes to performance, Intel Core Ultra delivers the fastest core performance in any thin and light laptop. Built on our innovative performance hybrid architecture, Intel Core Ultra delivers its most powerful performance and efficient cores yet, enabling you to do all the things you're used to doing with your PC more quickly and more efficiently than ever. By placing memory on package for the first time, Intel Core Ultra reduces the distance for complex signals and operations, ensuring the same performance per thread at half the power, so you can finish what you need to do without worrying about an extra charge. With Intel Core Ultra 200V series processors, every stage in the graphics pipeline has been improved and optimized, from generating triangles to shading to the final rendering, enabling 1.5 better graphics compared to our previous generation. Gaming has never been this powerful on built-in graphics. And finally, the NPU has been equipped with 48 TOPS to ensure significant sustained AI performance. And with a combined 120 TOPS of AI performance, Intel Core Ultra 200V series is the most capable AI PC processor. But it doesn't stop there. We are shipping 80 plus Intel Core Ultra Series 2 designs in 30 global retailers. And with over 500 models enabled by 2025, we are enabling the most extensive AI experience possible with a PC.
So these software are the enable the most extensive AI experience possible with PC. So these software might be upgraded for Intel Core Ultra series. I see. Maybe for some color grading or audio adjusting and face tracking things, and also writing I think that these kinds of things. Also, OBS is also in there.
AI experience possible with a PC. Intel Core Ultra 200V series processor. More powerful, efficient, and intelligent than ever before. Are you ready to unlock the extraordinary?
Okay.
Memory on pack.
Right. I got it, but not sure how it is used. Like NPU, right? NPU. NPU. And this month. Software, LPU software. Let's watch this.
This video is sponsored by Skillshare. If you've seen what feels like any tech announcement lately, you're probably already sick and
This bit is, do we really need NPUs now? I'm not sure
tired
it's
of hearing
all
about on-device AI.
Apple Intelligence.
Personal intelligence right where you...
And it turns out it's a bit of both.
Let's skip
Of parameters basically all at once. This is why Copilot
Copilot
Plus
is-
PCs require at least 16 gigs of RAM, and why iPhones with less than 8 gigs of RAM won't be eligible for Apple Intelligence at all. The amount of RAM directly impacts how smart of a model you can use on any given machine. Third, the NPU also needs its own ultra-fast cache to store the results of its billions of small calculations without having to talk to the main system RAM each time. And fourth, we can speed up these calculations. Allocating a lot of it to the NPU is a real trade-off.
You guys are always pushing us to give you more. You're always saying, more tops, Lisa, more tops.
That was AMD's CEO, Lisa Su, implying that Microsoft really pushed them to prioritize the NPU over adding something else like more CPU cores, for example. So to sum things up, we can see two pretty clear decisions made by the industry so far. First, while NPUs are growing in importance, they are still relatively minor parts of our chips. And second, they are clearly a higher priority in smaller devices and a lower priority in the bigger ones. There is a direct correlation with size, and this holds true beyond just the 4 Apple chips that we've looked at too. NPUs have been common in smartphones since 2017 already, for 7 years now, and they can be found in loads of modern smartwatches and even in chips powering tiny devices like the Meta Ray-Bans. Meanwhile, in PCs, they are just now starting to roll out. That's a pretty clear correlation, and now to understand why NPUs actually matter, let's take a look at the concept of accelerators. Your computer is a math machine. All it does is calculate things. Every pixel, every sound wave, every character of text at the end of the day is represented by your computer as a series of numbers, which it then does maths on. In the early days, all of this math was done on the CPU, a single general-purpose math machine. CPUs are built to be super precise and also flexible, so they can do any type of calculation that your computer could need, including really complex logic using huge numbers, etc. But computer scientists have pretty quickly realized that many calculations simply don't need this amount of flexibility or precision. Take graphics, for example. On a 4K display, you have roughly 8 million pixels, and you'd want to refresh these at least 60 times a second. That is around 500 million updates per second. Now, the math for calculating each and every pixel is super simple, but doing it 500 million times every second is quite the challenge. And this math is exactly what GPUs or graphics processing units are good at, with the best ones currently having over 10,000 compute units. These are much simpler than the big cores of your CPU, but they're designed to run in parallel so they can do a ton of small calculations very quickly. Beside GPUs, there's also tons of other accelerators, such as video encoders and decoders or image signal processors built into every phone to handle the math needed to make your cameras work, etc. The idea here is pretty simple. If a calculation has to be performed again and again and again, it might be more efficient to just build a brand new chip for it that is dedicated to this calculation than to have your CPU do it. And that brings us to the newest accelerator on the block, the NPU, an accelerator built to run the math behind neural networks. Neural networks have for years now been used, especially on mobile devices, to power everything from autocomplete on your keyboard to detecting which parts of an image count as background to be blurred in portrait mode, but also for detecting faces in Snapchat so filters can be drawn on them, or for powering more accurate and faster voice dictation, or for turning sensor readings into useful information like, I don't know, step counts or heart rates or crash detection, etc. Tim Cook, for example, has claimed that around 200 different models are running on the iPhone already today.
Oh, yeah.
To be clear, the vast majority of that actually predates the current generative AI hype, and while many marketing departments would now like you to believe that neural networks are somehow magic, the good news is that they're actually just math. Or depending on how you see things, that might actually be the bad news, because we're now going to have to do a little bit of math together. And I promise you, I kept everything as simple as possible. I even made a little neural network just for us. So welcome to the dumbest neural network possible. This is Martin's image recognition machine. Let's just call it MIM. Okay, so the point of this network is that you can feed it an image that consists of exactly 4 black and white pixels, and the network can then tell you if this image has a diagonal line either this way or that way. That's it. It's the tiniest, most primitive cousin of an image recognition model. The model consists of so-called neurons, which are really just memory cells that hold a number, and then these are arranged into layers, which are then connected. And these connections all have specific numbers called weight associated with them, which I'll explain in a little bit. So in our 4x4 image, let's assign a value to each pixel, 1 if it is white and 0 if it is black. This way we can express any of our images with just 4 numbers. We can take these 4 numbers and then input them into the first layer of our model, which we'll call the input layer for very obvious reasons. That's right, we've now given the model our image as an input. Meanwhile, the output layer has 2 neurons. I made it so that if the first one is at 1, it means that the image gets recognized as having a diagonal line like this. If the second one is at 1, then the diagonal line should go like this. And if anything else is shown, there is no diagonal line detected. So our 2 output neurons are configured to tell us if the diagonal line goes like this or like this. Hence, image recognition. And the calculation goes like this. Take the first value from layer 1, multiply it by its weight, and add it to the first neuron on layer 2. Then you do the same multiplication and addition if we take the second neuron and the simple networks.
So neurons,
now, of course, logic and so on. All of these features of a model are called parameters, and complex models can have over 1 trillion of them. That's right, over 1 trillion parameters. And figuring out all of the intricacies of these networks is done with a process called training, and that typically happens on some gigantic remote server farm. Once we have a model trained, though, we can start using it, potentially even on our own machines, and that's how we get to NPUs. And because you now know the basic math that this requires, you also know what the requirements for the NPU actually are. The calculation that you've already seen is called a multiply accumulate calculation, because you first multiply 2 numbers and then you add it to a node. Then you multiply 2 more numbers and you add that to the same node, and so on. You multiply and you accumulate, and that's basically it. In the real world, you might also be simple and repetitive, but we might have to do billions of them a second. So we really want highly specialized hardware with many loaded into memory with its potentially billions of parameters basically all at once. This is why Copilot Plus PCs require at least 16 gigs of RAM, and why iPhones with less than 8 gigs of RAM won't be eligible for Apple Intelligence at all. The amount of RAM directly impacts how smart of a model you can use on any given machine. Third, the NPU also needs its own ultra-fast cache to store the results of its billions of small calculations without having to talk to the main system RAM each time. And fourth, we can speed up these calculations dramatically by accepting lower precision. Precision in this case simply means how much memory a computer allocates to any given number. For example, the more decimals that you want the computer to store for the number, the more memory it will need. Precision costs memory. And because we typically want neural networks to just output some probabilistic guess instead of a highly precise answer anyway, we can kind of get away with lower precision, and that in turn speeds up our calculations massively. And there you have it, the 4 things that NPUs need to be optimized for. They need to be able to do many different calculations in parallel, so many little cores, they need a ton of RAM, they need a ton of cache, and they also need low precision. And if you think that this sounds an awful lot like what we've recently said about GPUs, then you're correct. This is why GPUs are very often used for running AI workloads. Since 2017, many GPUs have even had dedicated AI hardware built in, which NVIDIA, for example, calls tensor cores. A 4090 card has a whopping 512 of these tensor cores dedicated to AI, next to other graphics-focused cores, and by today, even integrated GPUs like the ones found on Intel Lunar Lake have plenty of AI hardware too. In fact, on Lunar Lake, the GPU actually has higher peak AI performance than the much-hyped NPU, and an NVIDIA 4090 card absolutely blows any current NPU out of the water in terms of raw AI performance. It is not even close. So in short, your GPU already is your primary AI chip when peak performance is desired. It has dedicated hardware and software for running neural networks. And developers already primarily target GPUs for any workload that needs peak performance from a neural network, like say tasks for video editing. NPUs, on the other hand, are much more about power efficiency than they are about peak performance. The NPU on the Snapdragon X Elite chip, according to Microsoft, consumes less than 5 watts of power even at full load. It is a low-power chip designed to run permanently in the background without having to spin up the main CPU or the GPU.
So NPU is like supporting CPU and GPU might be the good understanding of the general things. CPU, GPU, NPU, and NPU is less energy. Let's see.
This, by the way, explains why NPUs first became popular in mobile devices. On PCs, we've generally optimized for peak performance in the past, while mobile users have always had to prioritize power efficiency, especially given that they run tasks like crash detection, heart rate monitoring, and so on permanently in the background. So really the question for computer makers now is what kind of permanent, efficient neural networking workloads they can have that can run in the background that would really benefit from an NPU. Stuff like image generation or a chatbot running locally is often demoed, but I think this is actually kind of silly. Your GPU could probably run these tasks just as well as your NPU, and I bet that they're only used because they are the only features that regular consumers can actually understand. More compelling is stuff like real-time captioning and translations of audio playing on a computer, or for example Windows Studio effects that can blur the background, isolate your voice, cancel echo, etc. on the fly. You could easily use these for hours and do so on a battery, so using an NPU for them totally makes sense. So that's nice, but I don't think we've seen any real game changers in this category just yet. Instead, the most compelling candidate for an NPU by far was, of course, Recall, a system on Windows that takes screenshots of what you do every few seconds. It runs image recognition and optical character recognition software on each frame, and it creates a searchable database of everything on the fly, all running quietly in the background without absolutely nuking your battery. This is exactly the kind of task that an NPU would be exceptionally good for. Computation-wise, this is the absolute sweet spot for the NPU. It is a pretty complicated math problem, and yet it should happen quietly in the background basically all the time without the user even having to notice it. Now the question, of course, is whether people will at least eventually accept this kind of an intrusive system, or whether developers will at least come up with other tools that will be just as good of a use of an NPU as this. For now, I think the answer to both of those questions is not very clear, and so I also think that the value of the NPU is not overwhelmingly obvious either. Now, I don't know about you, but for me, seeing this wave of generative AI taking over everything has ironically only gotten me to care about creativity and actually what I've been making my thumbnails in recently. And I was watching this fantastic 6-hour Skillshare masterclass to make really good, and the platform is customly they've been neglecting over.
Okay, so what I got is NPU, there's CPU, GPU, and NPU, and CPU and NPU will be supported by NPU, and because of efficiency of energy, and I'm not sure. I got the general things. Alright. Let's watch another video. Can Intel survive the valley of death?
A few weeks ago, Intel announced that they'd lost $16.6 billion in a single quarter. This was by far the biggest loss in the company's history, and for context, it's about 22 times as big a loss as AMD made in profits in the same quarter. Now, some of this came from one-time costs, but that same week, Intel was also kicked out of the Dow Jones Index, where it was replaced by Nvidia. That's a position Intel lost after holding it for 25 years. Intel is having an unimaginably bad time, at the same time as the rest of the chip industry is going through perhaps its biggest boom ever. And yet, if you zoom into their stock price chart, you'll see something really odd. On the day that their catastrophic earnings were announced, their stock price actually jumped about 15%, showing that, perhaps unintuitively, there's actually a bet to be made. This chart shows a concept called the Valley of Death, which is usually used to describe a struggle that startups face. The startups have a bunch of resources like money, which they spend to develop their products and technologies before they can go to market. And if their tech is sufficiently expensive to develop, they might run out of those resources before they even get to have revenues. This valley is so deadly that many startups never make it to the other side. Now, Intel, of course, is hardly a startup. Just a few years ago, it was still the world's largest chip company. But after CEO Pat Gelsinger took over in 2021, he introduced a plan that was so audacious that it plunged the company into chaos and took what was once the world's largest chipmaker through a valley of death of its own. So far, we've definitely seen Intel go down as a result, and the fall has been extremely painful. The hope is that they might have hit rock bottom right around now, and the question is whether they'll ever be able to survive the climb out. This video is sponsored by Incogni. Combined. Meanwhile, ARM, the maker of the world's most successful CPU architecture, has about 6,000 employees. Today, each of these firms is individually worth significantly more than Intel, and yet Intel has more employees than all three of these combined. That might seem surprising until you realize that Intel has historically been a whole different class of a company. Compare, for example, Nvidia's Grace chips with Intel's competing Xeon 6. The former are designed by Nvidia, they're manufactured by TSMC, and they use ARM's instruction set architecture. Meanwhile, the latter are pretty much all made in-house by Intel. While TSMC, Nvidia, ARM, and most other modern chip companies focus primarily on one segment of the chip-making process, Intel had the complete chain in-house, and so it was a bit like having three of these companies rolled into one. This vertical integration is one of the many things that led to the company's downfall, but for many decades it was actually one of its biggest strengths. Because if all three of these parts actually work really well, then together they create incredible synergies. The x86 instruction set architecture was a bit like a shield for the rest of the business. See, ISAs are basically standards. They describe how a chip executes code or instructions on its most basic level. Once adopted, pretty much every x86 chip can technically run every operating system like Windows, macOS, and Linux, and also the millions of apps on top of those almost automatically. This is extremely convenient, but it also often makes switching away tremendously expensive, because it would often require having to rewrite tons and tons of software for a new standard. x86 was the dominant ISA for decades, and it was, to a large part, owned by Intel, who only had to share it with AMD, which overall created an incredibly comfortable situation for them. Their competition in CPUs was more or less reduced to a single company for many, many years. I mean, talk about a crazy defensive moat. Second, until about 2015, Intel had what were clearly the world's best chip foundries, which were consistently a generation or two ahead of other manufacturers like TSMC and Samsung. That meant Intel chips easily had 10, 20, 30% better power efficiency and performance just from manufacturing, which gave them a huge leg up versus AMD. I also had a call with the fantastic Patrick Kennedy from Serve the Home, who said that ARM chips were considered for servers already back in 2013, but were then disregarded because even if a competitor could beat Intel's designs, they couldn't do so enough to beat Intel's manufacturing. And by the way, if you want to learn more about the world of server chips, that's world-class designs. Rapidly. In 2005, Steve Jobs announced that the Mac was reportedly orchestrated by the bid on the right to make bit. x86, especially at a time when they did get 14 nanometers out 1 year later, but then they kept releasing chips with that until 2021. a whole 6 years later. And the next node properly.
So it might be the decline of Intel might be because of the M1 chips of Apple and also rise of Ryzen things maybe.
Zainic, a former process engineer under whom Intel took perhaps losing its central role in computing. Just look at how Qualcomm, for example, presents their phone chips. Their CPU is one of their least important elements. Instead, the image signal processor, the GPU, the hexagon neural processing unit, or the various wireless chips are all shown as more important. Similarly, Intel itself published this chart showing that the ratio of GPUs to CPUs is increasing relentlessly in the data center, and this was before the current AI boom even started. Meanwhile, Serve the Home recently went to film the data center.
So I think the what GPU capable of is something not the main thing, the high performance PC using like GPU is much more main things or need some power, and CPU is maybe good enough already, and GPU have more gap of what you can do, and the more of the GPU development you can do more, and the limitation things maybe more GPU you can do more, but more CPU it does not change much. I think that kind of things is the point.
That Elon Musk's X built for Grok AI, where you can typically see 3 to 4 GPUs for every CPU, an extremely profitable one, years into their troubles. A company like this can make mistake after mistake and just cover up the cracks that start forming. But then, of course, eventually there is a reckoning. The most immediate threat to Intel came from AMD, who'd been a distant second player for over a decade, suddenly becoming a serious competitor once Intel lost its manufacturing advantage. Change is slow, but this chart from Next Platform beautifully shows the relentless rise of AMD and the decline of Intel in the server space by revenue. Looking at all device categories, last quarter AMD already shipped 28.7% of desktop, 22.3% of laptop, and 24.2% of server x86 CPUs, with healthy gains across the board. But long-term, the even bigger threat to Intel came from the rise of ARM. Frustrated with Intel's slow progress, Intel took on the Herculean task of moving macOS to its own ARM chips. Microsoft, of course, is in the process of pushing for Windows on ARM, and servers started getting flooded with ARM chips too. Microsoft, Amazon, and Google, the three big cloud vendors, all built their own ARM-based server CPUs, and so did.
So Microsoft made own CPU and Apple made own CPU, and that makes Intel to go lower. And so Intel CPU will be the third party kind of things, like not main things on Microsoft, not the main thing on Apple. So it can be so replaced by Ryzen. So the value and specialty is not on Intel. That might be the reason of decline of Intel. I see.
NVIDIA and many others. ARM is suddenly everywhere, and if it gets enough adoption on PCs and servers, Intel could find its own x86 chips suddenly being the ones that struggle with compatibility. That is an existential threat that Intel might never recover from, and together with the troubles in manufacturing, it was time for a complete rethinking of the company. Pat Gelsinger was appointed CEO of Intel in 2021, and right away he was seen as a sort of messiah figure. Early in his career, he was the 5 nodes in 4 years now. That is less than 10 months for each node, which is so aggressive, it would see Intel surpass TSMC's chip making by 2025 if achieved. Nothing of the sort has ever been done before. He claimed that the company would not only need to figure out EUV, the key technology that partially broke their chip manufacturing, but that he would also pay almost anything to be the first to adopt high NA EUV, which is sort of the next, use that node to make millions of ultra profitable chips with it for years to make back their investment, but Intel didn't have time for that. that. They don't need this many nodes, especially when many of their chips are now made by TSMC, so some of them might only be used to make a single type of chip before the company basically moved on from it. So they're paying extra to rush the development of what is already one of the world's most complicated engineering challenges, then they're deciding to not use that, and instead they're also paying TSMC for using their really expensive services. That is tens of billions of dollars basically set on fire, and so Pat needed to find a lot of money very quick. Conveniently, he was running one of the world's largest companies, which somehow still made almost $80 billion in revenue the year Pat took over and was still extremely profitable. So right away, he changed that. The company under Pat simply started spending all of its money and more. Beside that, he also cut expenses by stopping to pay dividends, by starting mass layoffs, by closing businesses that were not making profits yet, etc. And Pat also sold off a whole lot of things. For example, Intel sold off 49% of one of their chip fabs in Ireland to a private equity fund, which netted them $11 billion. Mobileye, their self-driving car chip business, went public, raising Intel a good sum of money, as Intel sold a lot of their shares in it. Intel wants to sell a minority share in Altera, their FPGA unit, which they hope to raise billions, and so on. And finally, he of course convinced the Biden government to commit $19.5 billion in funding through the CHIPS Act, and also important TSMC is, that's a pretty exciting vision. His plan was to sacrifice just about everything for this vision, truly a valley of death. So, how's it going for them? Starting with manufacturing, progress has been mixed. On the worrying front, Intel has already cancelled its 3rd out of 5 nodes. The Arrow Lake chips that were supposed to be made with this Intel 20A process were instead made by TSMC. Now they tried to spin this as a positive of basically skipping ahead to 18A, which is a pretty similar technology, so maybe this is not a massive deal, but it's a significant wobble in a plan that can't really afford wobbles. The company also had to delay, or more likely cancel, their massive planned expansion to Germany with brand new fabs, which is probably a sign that they have less money than they hoped for. And similarly, funds from the Biden government's CHIPS Act keep getting delayed, and the new Trump presidency, of course, adds a whole lot of uncertainty to government support as well. All of this, combined with terrible earnings, caused Intel stock to massively underperform, which creates huge risks for Pat. If investors don't believe that the...
I think that's very scary. That I did not believe these things of Intel's decline would happen. But through the video, I got to know that the CPU and GPUs and GPU has more space to develop and easily, and that's why NVIDIA is developing so much. And also Intel has some struggle with competition. So for a while the GPU reached to some peak point, NVIDIA rise up, maybe. How do you think?
Intel stock to massively underperform, which creates huge risks for Pat. If investors don't believe that the plan is working, they can fire the CEO, and with such low valuations, other companies like Qualcomm are tipped to be interested in buying Intel or even stripping it for parts. The sharks are circling when they smell blood in the water, and Intel is definitely bleeding very heavily. Now, I don't think the US government would allow the company to be completely dismantled, to be sold off to a foreign buyer, for example, but a lot of bad things could happen. But meanwhile, on the positive side, Intel did complete the jump to Intel 4 and 3, its first 2 nodes. They did so roughly on time. Intel 4 successfully rolled out EUV, finally, and Intel 3 was used to make the company's new Xeon 6 server chips, which Patrick from Serve the Home tells me are finally really competitive, so theoretically this means that the manufacturing has to be pretty good. Intel claims that 18A, the 4th node, is on track. They say that defect densities are good, and they've already announced multiple external companies like Amazon, for example, who said that they'd be interested in making their own chips with it, because this should be Intel's first node that will be open to others. 18A is also the node where Intel claims that they'll finally start reaching parity with TSMC, more or less, so a lot is riding on this node, but of course we won't know how good it is until we actually see it. Okay, and moving on to design, that has been a pretty mixed bag too. Here's a list of their relatively recent chip families, and here's my very basic attempt at ranking them for how competitive they are overall without getting too much in the weeds. Xeon 6 seems very nice, and it's a sorely needed bright spot. Lunar Lake in my own testing has been pretty good, but not quite a home run. Meteor Lake was mostly disappointing, and Arrow Lake got pretty much demolished by the competition. So, mixed result for a company, especially as they were supposed to get a big boost from switching to TSMC, but then they're probably also wildly distracted by the restructuring, so maybe not unexpected. Now, based on all of this, I honestly don't know if Intel will make it out of the valley of the death, if yes, how well, or whether they'll be sold off for parts halfway through. But the other question worth asking is whether Pat deciding to go down this specific path was the right choice, because there's clearly also a second available path. Intel could have just chosen to accept defeat in manufacturing and could have chosen to find a way to sell off its fabs. AMD did exactly that when they spun off theirs and called them global foundries, while Nvidia, who never owned foundries in the first place, is now worth 33 times as much as Intel and 4 times as much as TSMC. Clearly, chip companies without fabs can thrive. And maybe selling off manufacturing would have allowed Pat to spend all of their time and energy on making sure that they actually designed world-class chips. That might have allowed them to beat AMD or to fight back against the ARM threat. Or the company could have prioritized their AI chip business with Gaudi. Nvidia is on track to sell about $60 billion in AI chips this year. AMD is looking at about $5 billion, while Intel will miss even its $500 million target. Intel could have focused on winning this market instead of focusing on trying to beat TSMC. It is still too early to say whether Pat's gamble will actually pay off, and to be fair, if it does, they could become one of the true giants of the industry. But this has been an extremely risky bet and also an extremely bumpy ride. Okay, and because you seem to enjoy hearing about corporate disasters, I want to tell you about another pretty insane one that you've probably missed. About 3 months ago, a company called National Public Data was breached and reportedly lost 2.9 billion records containing full names, current and past addresses, social security numbers, dates of birth, phone numbers, and more from citizens in the US, UK, and Canada. National Public Data is ironically a totally private company and one of dozens of data brokers that hoover up the entire internet to create profiles of you, without your consent of course, which they then sell to pretty much whoever is willing to pay. They themselves list investigators, background check websites, data resellers, and more. But we also know that even government agencies have decided that it's often easier to just buy data on you from data brokers than it is to do the spying themselves. But there's a silver lining to the story, which is that in these countries at least, you actually have the right to have your data deleted from, for example, a data broker, which apparently in the case of National Public Data actually worked. Quote, the database does not contain information from individuals who use data opt-out services. And Incogni's data removal service is what I use for this, and you can see that they've already successfully deleted me from over 80 such data hoarders so far. That is an insane number. Incogni finds which databases you are in, they send the requests on your behalf, they deal with objections, and they keep doing this even after you are deleted, so data brokers don't just add you back right again after they deleted you, which is why this is a subscription. They support multiple email addresses and 3 physical addresses with a single subscription, plus they're also family plans. Now again, the removal only necessarily works in places that have legal frameworks requiring it, but that's a pretty good selection already. To sign up, be sure to use my code TechOutR to get an exclusive 60% off an annual Incogni. Intel lost its manufacturing advantage.
So I now understand the sad decline of Intel. From now, maybe the GPU's development might be like NVIDIA will be the lead the AI and image generation kind of things, and that's why NVIDIA grows more and Intel is less. Maybe the point is the AI related tip, the development is the key of the industry. That's why NVIDIA grows more and more, and I think that keeps from now on. And the value of the capable of things is much more important rather important GPU rather than CPU because of the what things able to do with CPU is now it's something enough, and GPU has more space of development. I got to know that why Intel's go down. Now I understand that. And can Intel survive the valley of death? I'm not sure about the question, and how do you think about that? Please write the comment, and thank you for watching.
Right to make the chip for Apple's upcoming phone as well. Intel had recently bought a small ARM-based chip company it called X-Scale at that point, which might have been perfect for this, but Ottolini told Jobs that they wouldn't bid. x86 had just won and it had done so pretty decisively, so Ottolini was actually in the process of killing off their ARM business altogether in favor of a new project that the company called Intel Atom, a mobile chip, but one using x86. Now, perhaps it's understandable that Intel did not want to torpedo its own extremely profitable x86 monopoly, especially at a time when Apple's iPhone was not yet proven to be a success. But of course, now in retrospect, we know that that was one of the biggest missed opportunities in technology history. Once smartphones were inevitably the next big thing, Intel did try again, and they even managed to put Atom chips into some Android phones. That's right, you could get an Asus branded smartphone with an Intel Inside sticker if you really wanted to. But the company came late. It found that now it had compatibility issues, as most of the smartphone world had already standardized around ARM, and they never caught up. Smartphones were a typical case of the innovator's dilemma. Intel itself